On 27 June 1941, the logbook at Montreal Locomotive Works noted a first. The trial run of the tank, Canadian Ram Mark I. 12 months earlier, British formations had lost hundreds of tanks in France, and the United States, not yet at war, prioritized its own rearmament. Export approvals stalled. Commonwealth requests were placed behind domestic schedules. The expectation in London and Washington was simple. Canada lacked the heavy industry to design, cast, and assemble a modern medium tank. The test run contradicted the assumption. Using components derived from the M3 medium and a newly cast low-silhouette turret, Canada produced a complete armored vehicle line design, foundry, machining, assembly inside 18 months. By 1943, factory reports would list 1,900-plus ram hulls completed. Germany scarcely registered the program, until those same hulls returned as Kangaroo carriers, moving infantry through fire that had pinned them a month earlier. Ottawa, 10 July 1940. A memorandum crosses Prime Minister W. L. Mackenzie King's desk from the Department of Munitions and Supply. The subject line reads, British armored losses, France campaign, the numbers are stark. His Majesty's forces evacuated Dunkirk with fewer than 200 serviceable tanks. Tank production in Britain struggles under bombing and material shortages. American export licenses remain frozen behind neutrality laws. Minister C.D. Howe's response arrives within 48 hours. Cabinet minutes record his position. Canada must provision its own armored capability independent of external supply. The expectation across Whitehall and the War Office assumes Canada will wait for British designs, wait for American generosity, wait for the storm to pass. Reality moves faster. Major General Victor Odlum, commanding officer overseeing equipment acquisition, advocates loudly for domestic tank production. His argument hinges on a simple premise. Canadian Pacific Railway's Angus shops and Montreal Locomotive Works possess the heavy machinery, the skilled labor, and the industrial discipline to build complex mechanical systems. They build locomotives. A tank, he argues, is a tracked locomotive with armor. The technical pathway emerges quickly. American Locomotive Company, ALCO, produces drawings for the M3 medium tank. Canada negotiates access to these blueprints under the understanding that any derivative vehicle will serve training and Commonwealth purposes only. The Continental R975 radial engine, already in production for aircraft, can be adapted for tank use. Canadian foundries can pour armor plate. Machine tool suppliers can retool. By December 1940, requisition orders flow through the system. Over 350 precision machine tools, lathes, milling machines, boring equipment are redirected from locomotive production to armored vehicle work. Armor plate contracts go to Dominion Foundries and Steel, Dofasco, in Hamilton. Engine licensing agreements are signed. Floor space at Montreal Locomotive Works is cleared, and new jigs are designed. The contrast is profound. In June, Canada possessed no medium tank production capability. By year's end, the industrial architecture for series production exists on paper, in contracts, and in the minds of engineers who have never built a tank before. Montreal, 3 October 1940. Inside the drafting room at Canadian Pacific Railway's Angus shops, white overhead lamps illuminate rows of angled desks. E.J. Renault, chief engineer for the RAM project, leans over blueprints marked with turret ring diameters, gun mantlet profiles, and hull armor angles. His team numbers fewer than 20 designers, yet their task is to create Canada's first indigenous medium tank design within 6 months. The expectation from Allied planners is straightforward. Canada will import turrets from Britain or the United States, then mate them to hulls built domestically. Turret casting represents one of the most technically demanding aspects of armored vehicle production, requiring precise tolerances, heat treatment expertise, and quality control that few facilities worldwide can manage. Reality defies expectation. Dominion Foundries and Steel in Hamilton undertakes the challenge. By late October, the first experimental turret casting is poured. The specifications call for a low-profile design, eliminating the M3's vulnerable sponson-mounted guns in favor of a single fully rotating turret. The turret ring diameter is set at 54 inches, large enough to accommodate the British 2-pounder QF Mark 9 gun initially, with provisions for future upgrades. The engineering decisions embed flexibility into the design. Vertical volute spring suspension, VVSS, provides reliable tracked mobility across varied terrain. The transmission, a 5-speed manual unit, offers reasonable cross-country performance. Frontal armor is specified at 76 mm, equivalent to contemporary British and American medium tanks. Internal layouts prioritize crew efficiency, ammunition stowage, and radio integration using the British No. 19 set. Archival inspection sheets from November 1940 document an unexpected outcome. Tolerance measurements on the first turret casting exceed specifications. Foundry engineers achieve dimensional accuracy within 1/16 of an inch across critical surfaces, better performance than anticipated for a first attempt. Engineer sign-offs and gauge readings are preserved in production records. The turret success eliminates a critical bottleneck. With domestic casting capability confirmed, Canada controls its own production schedule. No longer dependent on transatlantic shipments subject to U-boat interdiction, the program proceeds on Canadian time, driven by Canadian resources. Design work accelerates through the winter. By February 1941, complete blueprint sets exist for hull, turret, suspension, drivetrain, and auxiliary systems. Component suppliers are contracted. Production tooling is fabricated. The first prototype hull approaches completion. Aberdeen Proving Ground, Maryland, 14 February 1941. United States Army Ordnance officers in winter uniform stand beside clipboards and stopwatches as the first Canadian Ram prototype completes its initial mobility trials. The Proving Ground's standardized test protocols measure acceleration, braking, cross-country speed, obstacle negotiation, and mechanical reliability across 50 miles of varied terrain. The expectation among observers is cautious skepticism. This is Canada's first attempt at a medium tank, a nation with no armored vehicle heritage, building a derivative design with improvised tooling. Mechanical failures, design flaws, and performance shortfalls seem probable. The test results tell a different story. Range books record a maximum road speed of 42 kilometers per hour, comparable to the M3 and superior to most British cruiser tanks. Frontal armor thickness measures 76 millimeters, providing protection against German 37 mm and 50 mm anti-tank guns at combat ranges. The suspension handles rough terrain without component failures. Engine temperatures remain within acceptable parameters. Ordnance Board comments, preserved in official test documentation. Note: mechanical performance satisfactory for training and reserve purposes. Minor turret defects observed. Hatch mechanisms require refinement. Optical alignment needs adjustment. The 2-pounder gun installation receives mixed reviews. American observers recognize that British doctrine, not Canadian preference, drove the armament choice. The gun's anti-tank performance is adequate for 1941 threats but offers limited high-explosive capability. Internal Canadian liaison reports document the subtext. The United States will not approve the Ram for export or lend-lease distribution. American production priorities focus on the M3 and its successor, the M4 Sherman. Britain's tank requirements will be met through American manufacturing, not Canadian derivatives. The Ram will not fight on the front lines as a gun tank in British or American service. Yet the Ordnance Board grants a crucial authorization: approval for production in training and ancillary roles. Canada receives permission to proceed with series manufacturing, not for combat deployment, but for crew instruction, tactical exercises, and home defense. The approval is narrow, but it is enough. The technical validation matters as much as the bureaucratic outcome. Aberdeen's tests prove that Canada can design, build, and deliver a functional medium tank meeting Allied standards. The industrial capability is real, not theoretical. The foundation exists for whatever comes next. Montreal Locomotive Works, 5 November 1941 through March 1942. The transformation of a locomotive factory into a tank arsenal proceeds with industrial logic. Overhead cranes that once lifted boiler assemblies now position tank hulls. Welders trained on railcar construction apply their skills to armor plate. Floor space measured in acres accommodates parallel assembly lines, with hull fabrication, turret installation, drivetrain integration, and final inspection proceeding in sequence. The production target is ambitious: 150 tanks per month by mid-1942. Unit cost is calculated at 55,000 Canadian dollars per vehicle, less expensive than importing equivalent British or American tanks, accounting for shipping, currency exchange, and delivery delays. Expectation among planners assumes component shortages will throttle output. The Ram depends on American-supplied Continental engines, transmissions, and precision parts. Any disruption in cross-border logistics could halt production for weeks. Reality demonstrates Canadian adaptability. When American carburetor castings arrive late, Canadian suppliers tool up to produce domestic alternatives. When transmission deliveries slip schedules, Montreal Locomotive Works increases buffer inventory and sequences production around available parts. Armor plate supply is synchronized with rail delivery windows, Dofasco ships on predictable schedules, and MLW staging areas never run empty. Monthly production reports document the ramp-up. November 1941, 14 complete tanks. December, 29 tanks. January 1942, 46 tanks. February, 68 tanks. March, 94 complete tanks, with 17 shipped to the United Kingdom for evaluation by British training commands. The factory operates on 3 shifts. Welders, machinists, inspectors, and assembly workers number in the thousands. Heat treat ovens run continuously, hardening armor plate and drivetrain components. Quality control inspectors stamp serial numbers, check tolerances, and sign off on acceptance forms. The rhythm of production settles into a sustainable cadence. Canadian substitutions keep the line moving. Domestic instrument panel assemblies replace imported versions. Radio installations adapt British sets with Canadian fabricated mounts. Minor modifications are absorbed without disrupting the master schedule. The workforce expansion tells its own story. In October 1941, Montreal Locomotive Works employed approximately 3,000 workers. By March 1942, that number exceeds 5,000. Training programs run continuously. Experienced machinists teach newcomers. Welding instructors certify armor plate specialists. Quality inspectors learn military specifications. The social transformation mirrors the industrial one. A civilian workforce becomes a military-industrial workforce. Labor relations remain stable despite the demanding schedules. War production bonuses, overtime pay, and recognition of essential war work maintain morale. Union representatives coordinate with management to sustain output while protecting worker safety. Accident rates remain below peacetime locomotive production levels, a testament to training programs and safety protocols. By the end of March 1942, Montreal Locomotive Works has delivered over 200 Ram tanks. The production system is validated. Crews are being trained. Spares provisioning is established. The industrial infrastructure of Canadian armored vehicle manufacturing is operational. In the same quarter, Germany expands Panzer III and Panzer IV production to sustain operations on the Eastern Front. But a dominion of 11 million people is narrowing the capability gap with factories, rail cars, and the discipline of mass production. Montreal, 24 April 1942. A Ram turret sits open on assembly trestles under the workshop lights. Machinists mark cut lines for a new mantlet aperture. The 2-pounder gun, adequate in 1940 but marginal by 1942, is being replaced by the British 6-pounder QF Mark III, a 57mm anti-tank gun with significantly improved armor penetration. The expectation is that changing the main armament will force redesign delays, retooling shutdowns, and production disruptions. Turret dimensions must accommodate the larger gun. Recoil mechanisms require recalibration. Ammunition stowage must be reconfigured. Internal layouts need revision. Reality demonstrates the foresight of the original design. The 54-inch turret ring was deliberately oversized to permit future upgrades. The Ram Mark II conversion integrates the 6-pounder without major structural changes. Mantlet modifications are manageable. Recoil clearances are verified. Ammunition racks are repositioned to hold 40 rounds of 57mm ammunition, fewer rounds than the 2-pounder configuration, but each with far greater hitting power. Gunnery test results from the Armored Fighting Vehicle School at Camp Borden document the improvement. Penetration tests against calibrated armor plate show the 6-pounder defeating 60mm of vertical armor at 1,000 yards, sufficient to engage German Panzer III's and early Panzer IV's frontally under combat conditions. First-round hit probability at 800 yards increases due to the flatter trajectory of the 57mm round. Internal memos circulate through the Department of Munitions and Supply, noting that the Ram Mark II achieves firepower parity with the early M4 Sherman. While the Sherman will eventually adopt the 75mm gun, offering better high-explosive performance, the 6-pounder Ram provides comparable anti-tank capability for training purposes. Canadian crews learning gunnery on the Ram will transition to the Sherman without relearning ballistics or engagement doctrine. Production lines at Montreal Locomotive Works absorb the Mark II changes seamlessly. By May 1942, new tanks roll off the line with 6-pounder armament as standard. Mark I tanks already delivered are scheduled for retrofitting during maintenance cycles. A turret swap operation completed in under 8 hours by trained crews. The ballistics manuals prepared for Ram gunnery instruction become templates for Sherman training. Range tables, penetration data, and engagement procedures translate directly between the two guns when Canadian units later adopt the Sherman's 75mm weapon. The intellectual infrastructure, how to teach tank gunnery, how to calculate firing solutions, how to conduct range estimation, is built on Ram foundations and carried forward. Production statistics through summer 1942 show the transition's efficiency. June output reaches 112 tanks, all Mark II configuration. July, 126 tanks. August, 139 tanks. The learning curve flattens. Workers master the new assembly sequences. Quality metrics improve. Delivery schedules remain predictable. The 6-pounder adoption reflects a broader pattern. Canada is not simply copying Allied designs. It is actively integrating improvements, adapting to changing battlefield requirements, and maintaining production momentum despite evolving specifications. By summer 1942, Canada fields a 6-pounder medium tank before the majority of M4 Shermans in British service receive the 75mm gun. The Ram Mark II is not a frontline weapon, but it is a thoroughly modern training vehicle, providing crews with realistic preparation for the tanks they will eventually take into combat. Camp Borden, Ontario, and Aldershot, United Kingdom, January through September 1943. Winter mornings at Camp Borden begin with cold start procedures. Instructors time crews on pre-operational checks, oil levels, track tension, radio function tests. The Ram's Continental R975 engine, reliable in moderate climates, demands careful priming in sub-zero temperatures. Drivers learn cold weather protocols, warming procedures, fuel mixture adjustments, battery management. The expectation among some training officers is that a non-combat tank will provide limited educational value, that crews trained on the Ram will require extensive requalification when they transition to frontline Shermans. Reality contradicts this assumption. The Ram's mechanical layout, driving characteristics, and gunnery systems closely parallel the Sherman's design. Both tanks use the Continental radial engine. Both employ vertical volute spring suspension. Both feature similar transmission designs. Crews mastering the Ram require minimal retraining when they transition to combat vehicles. Training records document the scale of the program. Thousands of Canadian tankers complete instruction on Ram series vehicles between 1942 and 1944. Courses cover driving, gunnery, communications, maintenance, and tactical employment. School records note mechanical availability rates above 90% during some training cycles, higher than many British schools operating with war-worn equipment. Average proficiency timelines show crews reaching competence in approximately 40 hours of combined driving and gunnery instruction. This pace matches or exceeds training timelines for crews learning on other Allied medium tanks. The Ram's reliability supports intensive training schedules. Vehicles can run multiple sessions per day without excessive breakdowns. At Aldershot in the United Kingdom, Canadian armored units arriving for final preparation before combat deployment continue training on rams until Sherman deliveries arrive. The transition is smooth. Drivers find the controls familiar. Gunners recognize the sight picture and ballistics. Radio operators use the same communication sets. Maintenance crews apply identical troubleshooting procedures. Attrition and accident rates in Canadian training are notably lower than comparable British programs. Fewer tanks are written off due to mechanical failure, crew error, or training accidents. The ram's robust construction and straightforward maintenance contribute to this record. Curriculum development mirrors the vehicle's capabilities. Gunnery instructors create standardized lesson plans. Driving courses establish competency benchmarks. Maintenance training produces field-qualified mechanics. The institutional knowledge, how to train tankers efficiently, becomes as valuable as the vehicles themselves. By mid-1943, Canadian training methods are studied by Allied armor schools seeking to improve their own programs. Documentation from the Royal Canadian Armoured Corps School preserves the evolution. Course syllabi from 1942 show experimental approaches, trial lessons, varying instruction sequences, uncertain timelines. By 1943, syllabi reflect refined methods, proven sequences, optimal instruction ratios, validated timelines. The RAM provides the stable platform on which training doctrine matures. By mid-1943, Canadian armored regiments possess a consistent pipeline of trained crews. Every driver, gunner, loader, and commander has learned on the same chassis. Standardization creates predictability. Doctrine, tactics, and crew coordination are developed on a common platform, then transferred seamlessly to combat vehicles. The training value extends beyond individual skill development. Canadian armor doctrine, movement techniques, fire coordination, combined arms integration is refined on the RAM during exercises at home and in the United Kingdom. By the time Canadian units land in Italy and Normandy, their tactical cohesion reflects hundreds of hours of collective training on vehicles that taught them how to fight together. Ottawa and Detroit, June through December 1943. Rail flat cars cross the Ambassador Bridge and roll through Windsor, Ontario, carrying crates stenciled for engines, transmissions, and radio equipment. The RAM production program depends on American component suppliers, yet the relationship is not one of simple dependency. It is a carefully orchestrated industrial partnership that demonstrates the integration of North American manufacturing. The expectation among some planners is that different national production plants will generate non-standard parts, creating logistical nightmares and incompatibility problems. Reality demonstrates remarkable interchangeability. The Continental R975 engine used in the RAM is identical to units installed in M4 Shermans. Transmission assemblies are sourced from the same suppliers. Vertical volute spring suspension components, bogies, springs, shock absorbers, are interchangeable across Canadian and American medium tank designs. Gun sights, periscopes, and optical equipment meet common Allied standards. This standardization simplifies logistics at every level. Spare parts for the RAM can often substitute for Sherman components. Maintenance procedures taught on one vehicle apply to the other. Field repair crews transitioning from Rams to Shermans bring familiar tools and familiar procedures. Contract summaries preserved in Canadian procurement records detail the scale of cross-border trade. Engine deliveries number in the thousands. Transmission contracts reach into nine-figure Canadian dollar totals. Radio suite procurement, British number 19 sets manufactured under license, follows predictable monthly schedules. Shipping manifests document the tonnage moving across the border. Steel, rubber, electrical components, precision instruments. The industrial alliance extends beyond simple parts purchasing. Canadian and American engineers consult on design modifications. Production techniques developed at Montreal Locomotive Works are shared with American factories. Quality control standards are harmonized. When problems arise, a batch of defective transmissions, a supplier delay, both nations' procurement offices coordinate solutions. Technical liaison officers maintain permanent posts in Detroit, Cleveland, and Montreal. Their correspondence files preserve real-time problem solving. A Canadian request for expedited engine shipments, an American query about armor plate specifications, a joint decision to standardize electrical connectors. The bureaucratic machinery functions because both nations recognize mutual benefit. Statistical summaries from late 1943 document the supply chain's efficiency. Component delivery schedules maintain 95% on-time performance. Quality rejection rates remain below 2%, comparable to domestic American production. Cross-border transit times average 72 hours from American supplier to Canadian assembly line. The system works. By late 1943, the RAM production line at MLW operates as an extension of the broader Allied armored vehicle manufacturing base. Components flow north, completed tanks move to training centers, and the system functions with industrial efficiency. The shared standards have strategic implications. When Canadian armored units deploy overseas, their maintenance infrastructure integrates seamlessly with American supply chains. A Canadian regiment operating Shermans can draw spare parts from American depots. Repair procedures learned on Rams apply directly to field maintenance under combat conditions. The technical language, part numbers, specifications, tolerances is universal. The Ram, though never a combat export, becomes the logistical dialect that Canadian armored forces speak fluently. They understand American mechanical systems because they trained on vehicles built with American components. They troubleshoot problems using American diagnostic procedures because those procedures were taught on Ram tanks in Canadian training centers. London, for October 1943. A War Office memorandum bearing the stamp Sherman adopted as Commonwealth standard crosses the desks of Canadian liaison officers. The decision is final. The M4 Sherman will equip all British and Commonwealth armored formations for frontline combat. The Ram, despite its training success and production achievements, will not serve as a gun tank in European operations. The expectation is straightforward. The Ram will be retired to depots, cannibalized for spare parts, or relegated to static defense roles in Canada. Hundreds of vehicles represent significant investment, but military necessity demands standardization on the Sherman platform. Reality takes an unexpected turn. Canadian staff officers at 1st Canadian Army Headquarters propose alternative uses for surplus Ram chassis. The vehicles are mechanically sound, mobile, and possess frontal armor equivalent to any Allied medium tank. Removing the turret creates a platform adaptable for multiple specialist roles. Proposals circulate through engineering offices and operational planning cells. Ram hulls can be converted to armored recovery vehicles, AR versus, equipped with winches, towing gear, and repair equipment. Observation post variants, OP tanks, can carry forward artillery observers, providing protected mobility and radio communication to coordinate fire support. Another concept emerges: armored personnel carriers. Infantry commanders face a persistent problem across all theaters. Assault infantry advancing under fire suffer heavy casualties. Truck-mounted troops are vulnerable to artillery and machine gun fire. Soldiers riding exposed on tank decks face similar risks. No Allied formation fields a dedicated armored vehicle designed to transport infantry across beaten zones and deliver them intact to assault positions. Staff Memo DMS-43-12, dated late October 1943, recommends adaptation of surplus Ram chassis for troop-carrying roles. Engineering feasibility studies examine the conversion requirements: turret removal, installation of troop benches, modification of hull roofs for infantry egress, retention of frontal armor and mechanical systems. The concept is not entirely new. Experimental armored troop carriers have been tested by multiple armies, but no Allied force has committed to large-scale production and doctrinal integration. The Ram conversion offers a solution using existing hulls, reducing production timelines and material costs. Design work proceeds through November. Engineers calculate capacity. 11 infantry with full equipment can fit comfortably in the deturreted hull. Bench configurations are tested. Dismount sequences are timed. A commander's position is established with visibility for navigation and tactical control. A heavy machine gun mount, typically a .50 caliber Browning, provides local defense capability. Trial conversions begin in December 1943 at Canadian workshops in England. The first vehicles undergo mechanical testing, capacity verification, and tactical evaluation. Infantry platoons practice embarkation and dismount drills. Armored squadron commanders assess integration with tank formations. Artillery observers test the OP variant's communication equipment and visibility. By December 1943, authorization is granted for pilot conversions. Workshops receive instructions to remove turrets from selected ram tanks, fabricate bench seating for infantry, and install hull roof hatches for rapid dismount. A heavy machine gun, typically a .50 caliber Browning, is retained for local defense. Radio equipment allows coordination with supporting armor and artillery. The converted vehicles retain the ram's mobility, protection, and mechanical reliability. Infantry capacity is approximately 11 soldiers per vehicle, enough for a full rifle section. Dismount procedures are practiced and refined. The concept shifts from theoretical to practical. The decision that ended the ram as a gun tank creates the chassis that will redefine Allied infantry mobility. Industrial capacity built to manufacture medium tanks now pivots to solve a tactical problem that has plagued every infantry attack since Normandy's hedgerows. Normandy, 7 through 17 August 1944. Workshops of 1st Canadian Army operate under camouflage netting in orchards south of Cannes. Cutting torches hiss as technicians remove turrets from ram and priest self-propelled gun hulls. Welders fabricate bench seating. Radio operators reposition communication sets for infantry use. Heavy machine guns are mounted on pintle fittings. The operation is improvised, urgent, and driven by battlefield necessity. Operation Totalize, the planned breakthrough toward Falaise, requires infantry to advance across open ground under German anti-tank and machine gun fire. Previous attacks have demonstrated the cost. Companies reduced to platoon strength, assault momentum bleeding away as infantry casualties mount faster than objectives can be seized. Lieutenant General Guy Simons, commanding 2nd Canadian Corps, directs the conversion program. His staff calculates that armored carriers can reduce infantry casualties by 50% or more during approach phases. Speed is essential. Totalized launches in days, not weeks. The expectation is that improvised carriers will be slow, vulnerable, and difficult to coordinate with armored formations. Critics question whether infantry will dismount effectively under fire, whether vehicle capacity is sufficient, whether mechanical reliability will hold. Reality proves otherwise. The first Kangaroos, named informally by troops who appreciate the vehicle's ability to hop infantry forward, complete field trials on 9 August. Capacity is confirmed at 11 infantry per vehicle. Dismount drills are practiced. Drivers rehearse movement formations. Radio coordination with supporting armor is tested and validated. Technical specifications are finalized rapidly. Each Kangaroo retains the Ram's 76mm frontal armor and Continental R975 engine. Maximum road speed remains 42 km per hour, sufficient to maintain pace with tank squadrons during advances. The .50 caliber Browning machine gun provides suppressive fire during approach and dismount phases. Radio sets, British number 19 or Canadian number 52, allow communication with infantry battalion headquarters and supporting armor. Crew organization settles into doctrine. Each Kangaroo is commanded by an armored corps corporal or sergeant, with a driver and machine gunner. The crew coordinates with the infantry section commander to plan routes, identify dismount points, and execute tactical movement. Trust develops through repeated exercises. Infantry learn to rely on their crews. Crews learn to anticipate infantry requirements. On the night of 7 through 8 August, Kangaroos move infantry forward for the initial totalized assault. 76 converted vehicles carry infantry of the 4th Canadian and 51st Highland Divisions across fire-swept ground. German machine guns engage, but .50 caliber armor defeats small arms fire. Infantry dismount at designated positions, assault objectives, and consolidate gains. After-action reports document the impact. Casualty rates during approach phases drop measurably compared with previous operations. Infantry arrive at start lines organized, equipped, and ready to fight, not scattered, depleted, and demoralized by losses during the advance. Commanders note the Kangaroo's ability to keep pace with tank squadrons, maintaining combined arms cohesion through the depth of the attack. German reports from defending units express confusion. Intelligence summaries note armored personnel wagons of unfamiliar type, delivering infantry in organized waves. The Kangaroo disrupts German defensive planning, which anticipates truck-mounted infantry vulnerable to pre-registered artillery fire. Mechanical performance exceeds expectations. Kangaroos prove reliable, mobile, and easy to operate. Maintenance requirements are manageable. Fuel consumption, though higher than trucks, is acceptable given the tactical advantage. Infantry units request more carriers. Armored regiments integrate Kangaroos into movement plans. The psychological impact on infantry morale is documented in unit war diaries. Soldiers express confidence in protected movement. They know they will reach assault positions alive, organized, and ready to fight. Officers report improved assault performance as infantry arrive at full strength rather than depleted by approach casualties. By mid-August, the Kangaroo concept is validated. Workshops accelerate conversions. Additional ram hulls are diverted from training duties. Priest chassis from re-equipped artillery units are converted. Within weeks, 1st Canadian Army fields over 100 armored personnel carriers. The ram hull, rejected for combat as a gun tank, relegated to training and ancillary roles, has found its battlefield purpose. Not as a weapon platform, but as a protective envelope that allows infantry to survive the approach and arrive ready to fight. Scheldt Estuary, 2 through 28 October 1944. The landscape is water, mud, and narrow causeways. 3rd Canadian Infantry Division faces the task of clearing German positions blocking access to Antwerp's port facilities. The terrain negates conventional advantages. Tanks bog in flooded polders. Infantry advance along exposed dikes under machine gun and mortar fire. Artillery support is constrained by limited observation. Kangaroos prove essential. The carrier's tracked mobility allows movement through soft ground that traps wheeled vehicles. Armored protection shields infantry during exposed advances across causeways. Shuttle operations ferry assault troops forward, evacuate wounded, and resupply forward positions, all under fire that would shred truck-mounted logistics. The expectation among German defenders is that soft terrain will channel Allied infantry into predictable kill zones. Machine gun positions cover causeway approaches. Mortars are pre-registered on choke points. The defensive plan assumes Allied infantry will advance dismounted, vulnerable, and slow. Reality contradicts German assumptions. Kangaroos deliver infantry directly to assault positions, bypassing much of the beaten zone. Tracked mobility allows flanking maneuvers through terrain Germans consider impassable. Armored protection reduces casualties during approach phases, ensuring assault platoons reach objectives at full strength. War diary entries from 3rd Canadian Infantry Division note: losses minimal relative to exposure. Kangaroo crews maintaining shuttle operations despite sustained indirect fire. Infantry morale notably high, troops confident in protected advance. After-action reports credit the carriers with enabling operations that would have stalled under conventional dismounted assault. Operational statistics document the advantage. Casualty rates for infantry attacking with Kangaroo support average 30% lower than comparable attacks using truck transport or foot movement. Time from assembly area to assault position decreases by 40 to 50%. Infantry arrive organized in section and platoon formations rather than scattered by suppressive fire during approach. German signal intercepts, captured post-war, reveal defender confusion. Reports from 2nd SS Panzer Corps mention armored personnel wagons of unfamiliar type arriving in waves. Intelligence officers attempt to classify the vehicles, uncertain whether they represent a new American design or a British modification. The ram-based Kangaroo remains unidentified in German intelligence assessments through the end of the Scheldt operations. Tactical innovation compounds the carrier's effectiveness. Infantry commanders develop leapfrog techniques. One wave dismounts and secures an objective while Kangaroos shuttle back for the next wave. The vehicles enable depth in attacks, sustaining momentum across multiple phase lines. German defenders face continuous pressure as fresh infantry arrive protected while exhausted defenders hold positions under sustained assault. Engineer units coordinate closely with Kangaroo operations. Armored Vehicle Royal Engineers, AVRES, based on Churchill tank hulls, clear obstacles and lay fascines. Ram-based observation post tanks provide forward artillery observers with protected mobility and reliable communications. The system integrates engineers breach, Kangaroos transport, infantry assault, artillery supports. Tempo increases measurably. Control of canal crossings and causeways improves as infantry maintain momentum. German counterattacks face consolidated positions rather than scattered, depleted platoons. The operational advantage compounds. Success breeds success, while German defenders fight isolated actions with diminishing support. Maintenance records reveal the Kangaroo's reliability under extreme conditions. Operational availability rates exceed 80% throughout the Scheldt campaign despite mud, water, and continuous use. Crew reports note that the Continental engine performs well in cold, wet conditions. Track maintenance requires attention, but no more than standard tank operations in similar terrain. By late October, the Scheldt operations validate the Kangaroo concept across the most difficult terrain Allied forces have encountered in Northwest Europe. The carrier is not a universal solution. Infantry still fight dismounted, casualties still occur, battles remain brutal. But the Kangaroo solves the specific problem of getting infantry across beaten zones alive and organized. Conversion programs accelerate. 1st Canadian Army workshops receive additional ram hulls from training centers in the United Kingdom. Priests continue to be modified. By November 1944, Kangaroo availability allows routine armored infantry operations, no longer an improvisation, but a doctrinal capability. Rhine crossings, March 1945. Maps on folding tables show phase lines, artillery fire plans, bridging sites, and assault timings. 1st Canadian Army operations orders integrate Kangaroos as standard elements, not special equipment requiring separate planning, but organic components of combined arms operations. The expectation in early 1945 is that assault river crossings will produce heavy casualties, particularly for infantry advancing to secure bridgeheads. The Rhine represents Germany's final major defensive barrier in the west. Crossing sites face prepared positions, interlocking fields of fire, and determined defenders. Reality demonstrates the maturation of Allied armored mobility doctrine. Kangaroos deliver assault infantry to river crossing points, then shuttle follow-on waves across pontoon bridges once engineers establish spans. Protected lift reduces casualties during approach and redeployment. Infantry platoons arrive at objectives intact, maintaining combat power through sequential phases of the operation. Ram-based armored recovery vehicles support the advance by recovering disabled tanks, towing damaged vehicles from blocking positions, and keeping supply routes clear. Mechanical reliability of Ram-derived chassis ensures recovery assets remain available throughout extended operations. Recovery statistics from 1st Canadian Army note that 73% of disabled tanks are returned to service within 24 hours, rate superior to formations lacking dedicated armored recovery capability. Observation post variants. Rams with turrets removed and replaced by radio-equipped observation posts provide forward artillery observers with protected mobility. Fire support coordination improves as OP tanks maintain pace with advancing armor, adjust fire in real time, and communicate target data without delays inherent in dismounted forward observer operations. Artillery response times decrease from 15 minutes to under 5 minutes for priority targets. Formation logs collate statistics that reveal operational tempo. Advance rates reach double-digit kilometers per day where terrain and resistance permit. Fuel consumption for armored infantry operations increases, but logisticians adjust supply plans to sustain the pace. Daily vehicle status reports show Kangaroo mechanical availability consistently above 85%, remarkable for vehicles operating intensively under combat conditions. Engineer reports credit protected infantry lift with maintaining momentum during consolidation phases. Traditional assaults stall when depleted infantry cannot hold gains against counterattacks. Armored delivery ensures sufficient infantry arrive to defend captured ground. allowing engineers to improve positions and prepare for subsequent advances. Doctrine codifies lessons learned from 8 months of operations. Staff procedures for Kangaroo employment are published and distributed. Infantry battalions train dismount procedures as routine drills. Tank squadrons coordinate movement with carrier platoons as standard practice. The organizational learning, how to plan, execute, and sustain armored infantry operations, becomes institutional knowledge. Allied observers from American, British, and Polish formations study Canadian Kangaroo operations. After-action reports are shared. Tactical lessons are disseminated. Requests for similar conversions flow through Allied logistics channels. The Canadian innovation becomes an Allied capability as other nations adopt the concept using their own surplus tank hulls. Production statistics from early 1945 document the scale. Over 400 Kangaroos are operational across 1st Canadian Army by March. Monthly conversion rates exceed 30 vehicles as workshops refine procedures and reduce turnaround times. The industrial system that built rams now sustains the Kangaroo fleet. Spare parts, maintenance schedules, and crew training all function as established processes. By late March 1945, armored infantry mobility is doctrinal practice across 1st Canadian Army. Staff officers plan operations assuming Kangaroo availability. Infantry battalions train dismount procedures as routine drills. Tank squadrons coordinate movement with carrier platoons as standard practice. The system functions not perfectly but effectively. The operational advantage is cumulative. German forces face Allied formations that maneuver faster, sustain fewer casualties during movement, and maintain unit cohesion through extended operations. Allied infantry no longer advance as vulnerable targets but as protected assault forces delivered by armor to positions where their combat power can be applied decisively. In the same weeks, German tank production contracts to a trickle. Industrial bombing, material shortages, and transportation disruptions strangle output. But the decisive factor is not German weakness. It is Allied strength expressed through industrial capacity converted to battlefield advantage. Ottawa and London, September through December 1945. Final ledgers close at the Department of Munitions and Supply. Summary tables are typed, verified, and filed in archives that will preserve Canada's wartime industrial record. The Ram tank program, begun in desperation and uncertainty in 1940, concludes with production totals that surprise even those who managed the effort. The expectation among some observers, those who remember the skepticism of 1940, is that without combat laurels, the Ram will leave no significant mark on military history. Training vehicles rarely earn recognition. Derivative designs seldom merit study. Reality presents figures difficult to ignore. Approximately 1,948 Ram tanks were produced at Montreal Locomotive Works between 1941 and 1943. In parallel, Canada manufactured 1,894 Grizzly cruiser tanks, Canadian-built M401s, demonstrating expanded production capacity. Thousands of conversions followed: Kangaroos, armored recovery vehicles, observation post tanks, specialized variants. Employment records document the human scale. Over 17 production plants and component suppliers participated in the program. Thousands of machinists, welders, inspectors, and assembly workers gained skills in precision manufacturing and armored vehicle production. The cumulative value of Canadian armored output reaches billions of Canadian dollars in wartime currency, investment that created industrial capability extending beyond any single vehicle program. Post-war munitions summaries, prepared for parliamentary review, highlight a remarkable timeline. Industry created from zero capacity to series production within 18 months. The achievement is administrative as much as technical, coordination of suppliers, tooling procurement, workforce training, quality control, and logistics accomplished while the nation simultaneously expanded its naval, air, and general munitions production. Allied forces codify lessons learned from Kangaroo operations. Protected infantry mobility becomes a recognized requirement in armored warfare doctrine. Post-war vehicle development programs in multiple nations pursue purpose-built armored personnel carriers, but the operational concept is validated by Canadian improvisation in 1944. Canada retains a heavy industrial skill base after the war. Plants that built tanks pivot to locomotive production, but the workforce carries forward expertise in welding, machining, metallurgy, and precision assembly. The organizational knowledge, how to manage complex production programs, integrate supply chains, maintain quality, persists in Canadian manufacturing. The strategic impact is institutional as much as tactical. Canada demonstrated the capacity to independently design, produce, and field major weapon systems, capability that reshapes Commonwealth defense relationships and establishes credibility in post-war industrial collaborations. Kingston, Post-War Analyses, 1950 through 1951. A Ram Mark II sits on the museum floor of the Royal Military College, its 6-pounder gun silent, its armor bearing the scuffs of training exercises but not combat. Engineering cadets study the vehicle during technical instruction, measuring tolerances, examining weld quality, and analyzing the design decisions that shaped Canada's first Indigenous medium tank. The expectation for expedient wartime production is rapid degradation, hurried manufacturing, substitute materials, and compromises driven by urgency should show in post-war condition assessments. Reality defies this expectation. Armor integrity remains sound. Castings show no stress fractures. Drivetrain components, properly stored and maintained, remain serviceable. The vehicle that was built quickly was built well. Testament to Canadian industrial discipline and the skills of workers who transitioned from locomotives to tanks without sacrificing quality. Continuity traces forward through post-war projects. The Badger Armored Personnel Carrier Program draws on Kangaroo operational experience. Canadian contributions to early Centurion tank support practices reflect lessons from RAM-based recovery vehicles and observation post coordination. The institutional knowledge, how to design, produce, and field armored vehicles, persists in Canadian defense industries. British post-war reviews, declassified in later decades, include assessments of Commonwealth industrial contributions. A 1951 summary notes, Canada demonstrated capacity to produce complex weapon systems independently of Empire supply networks. The RAM program validated Dominion capability for major weapons production under autonomous direction. The recognition is official, bureaucratic, and understated, yet it acknowledges a transformation. In 1940, Canada depended on external suppliers for every category of major weapons. By 1945, Canada manufactured tanks, aircraft, ships, artillery, vehicles, and munitions at industrial scales that placed the nation among significant Allied producers. The RAM itself served thousands of Canadian tankers who trained on its chassis, learned gunnery through its sights, and mastered tactics in its cramped interior. Those crews carried forward to combat in Sherman's the confidence and competence built on RAM foundations. The training value alone justified the program, but the Kangaroo conversions proved the hull's lasting contribution exceeded any single role. Germany regarded Canada as a supply appendage, a resource base lacking industrial sophistication or independent capability. The RAM proved otherwise not through battlefield victories, for it never fought as a gun tank, but through industrial achievement and tactical innovation. The final image is quiet. A tank that did not fire its gun in anger, yet changed how Allied armies moved infantry through fire. A chassis built in desperation that became a school for tankers and a platform for innovation. A symbol of industrial capacity translating into battlefield advantage. The RAM stands as evidence that free nations, possessing will and means, are capable of creating capability when necessity demands, and that sometimes the greatest contributions are measured not in enemies destroyed but in comrades brought home alive. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.